Welcome to today's KWK talk. To formally welcome you all, I call upon the Director of JNP, Dr. Guru Prasad.
Respected Professor Rajesh Gopakumar, Director ICTS, faculty members from there, students from there, ladies and gentlemen, and welcome to yet another lecture in the series Kaapi with Curiosity. Normally, I do a very short formal welcome, but I feel my role today is a bit privileged, I would say, because none other than Professor Rajesh Gopakumar, the director of ICTS, has come here to deliver a talk on a very, very thrilling subject, I would say, why strings. I don't want to preempt anything about string theory or such things. So, anyway, all of you know that Kaapi with Curiosity, KWK, is a joint endeavor, okay, hosted at JNP, and it's a joint program of ICTS and JNP. Today, to deliver this talk, none other than Professor Rajesh Gopakumar, who is the director of ICTS, is here. And a person of his stature has come here to deliver a talk. Means I'm really privileged, sir, to welcome you. Okay, thank you very much. Before I hand over the mic to Sharanya again for announcement, let me make a very brief announcement that in JNP, every year we have a lecture series called Dasara Lectures, modeled on Christmas lectures of Michael Faraday. There will be normally 4 lectures on a common theme. Last year it was the origins, and this year the theme is carbon. Okay, in that we have scheduled 4 talks on 11th of October, 12th, 18th and 19th. We have 4 lectures on 4 facets of carbon. Okay, one on carbon and the origin of life and our life as we know it, carbon and quantum science and technology, carbon and climate change, and carbon and its compounds, organic chemistry. So kindly do attend those lectures. We will send you more details actually. So thank you very much. Once again, welcome, sir. Welcome for this program. It is quite formal. That's why I'm telling you. Otherwise, you are one of the initiators of this. Thank you very much, Sharanya. Over to you.
Thank you, sir. I invite Dr. Pallavi Bhatt to introduce the speaker.
Welcome, everybody. Firstly, I would like to take this opportunity to thank JNP and Dr. B.R. Guruprasad for hosting these lectures over here. And I would also take this opportunity to thank Ms. Sharanya for her help in coordinating these efforts. Coming to the lecture today, it's an honor and great pleasure to introduce the speaker today, Professor Rajesh Gopakumar. Let me tell you a little bit about his journey. So it began with an unusually bold step of first of all topping IIT JEE exam in his year and then choosing to do physics instead of engineering, which is kind of away from the norm. And then he did integrated masters at IIT Kanpur, and after that he earned his PhD in Princeton University in 1997, and he did this with under the guidance of eminent physicist David Gross. And then he did a stint of research associateship at Harvard, and then returned to India in 2001 and joined at HRI, which is Harish Chandra Research Institute at Allahabad. And then he became full professor over there. And in 2015, he took on the leadership at ICTS. And he was committed to building a vibrant home for theoretical sciences in India. And under his leadership, the institute has grown, and it has earned a great reputation and reach. And his motto is discover in India. And this is rooted in the belief that serious world-class inquiry can happen in India and not just in the West. And now coming to his research front, he has made foundational contributions to string theory and quantum field theory, and he has introduced what are known as Gopakumar-Vafa invariants, Gopakumar-Vafa dualities, and he has asked these very interesting deep questions in many fields. I would like to just give you a sketch of these fields, which is ADS-CFT correspondence, minimal model holography, large and gauge theories, topological string theory, and duality with Chern-Simons theory. And he's earned many, many recognitions. And some of them I just would like to mention. Shanti Swarup Bhatnagar Award, ICTP Prize, and the World Academy of Sciences Prize, G.D. Birla Prize, and he holds many national fellowships. He is the Fellow of Indian Academy of Sciences, INSA, and the World Academy of Sciences. But beyond these accolades and his technical prowess, one of the most endearing qualities about him is his conviction that doing science is fun, that play and curiosity lie at the heart of any serious inquiry. He also has spoken many times about how he values this joy of exploration, and that institutions should not come in the way of that. And now I've been at ICTS for 4.5 years. I've seen him for that time, and I find him kind and thoughtful, and he really believes in empowering his younger colleagues so that they can do their best. And though he is busy as the director, he's always the person asking the most penetrating questions in any scientific talk. With that, I would like to now make a small gesture, and we would like to present him with a small memento. And with that, I would now like to pass on the stage to Professor Rajesh Gopakumar, and please join me in inviting him to the stage.
Thanks very much, Pallavi, for a very kind, very generous introduction, quite touched by your words. Thank you everyone for coming on a Sunday afternoon to this Kaapi with Curiosity. I'd like to firstly thank Dr. Guru Prasad, who has been our partner in this journey of ICTS and the Planetarium. I think the Planetarium is a very special institution of Bangalore, and so it has been a privilege, I think almost 10 years maybe now since we started this. Dr. Shailaja and I think was the head at that time, and she also had received it with great enthusiasm. Dr. Madhusudan, I mean everyone at the Planetarium, and now new people who are involved, I think have been working very closely, and we have I think it is not very often easy for institutions to collaborate, but I think on both sides there has been goodwill, and so this has continued, and I hope it will continue for many more years. And I also want to say that this journey in a way together has been also very fruitful, because when we started, we were in the basement of the old building, which was, of course, a very homely place, but nothing like this wonderful new complex that has been set up. And I think the planetarium itself, I think the government has appreciated its role in the many outreach activities that it conducts. And this is a great addition to the science outreach of Bangalore. So it has been a privilege to collaborate. So coming to the topic of today's talk, I wanted to, this question, I framed the talk in terms of this question because very often people ask me what is string theory and so on, which of course I try to explain in some ways, but sometimes people are very puzzled. I can explain what is string theory, but to explain why do people think about strings? Why is it that this notion came about? Why is it that people are studying it so intensively? And even though it's a very theoretical notion, I want to convey in this talk that it is not something just some fantasy of some theoretical physicist just thinking that, oh, let us consider some string-like objects and solve all the problems of theoretical physics. It's not like that. It's the strings originate very naturally from the theories that we have understood of nature, and I will try to explain that. In fact, in some ways, it goes back to the ideas of Maxwell and Faraday. Dr. Gurush Prasad mentioned the Faraday lectures. Faraday was a remarkable character who will feature in our talk today. So I will try to trace, in some sense, the origin of these ideas of string theory in things that are well rooted in ideas that we understand, but at the same time taking it in a completely new direction. And so I'll try to explain the magic behind that in some sense, why there is this very remarkable, how it very remarkably ties together many different things. So very often nowadays, especially in the popular discourse, there are people say, oh, string theory, oh, it's just some idea, some theory that no one believes, and so on. But I want to give you a little more of that nuanced idea by showing why it's very natural, and it's a framework that arises in nature, and why studying it has already led to so many important understanding, and that is only going to grow in the future. So that's the broad goal of this talk. So I'll have to start by telling you a little bit about the fundamental interactions. Many of you will probably know all this, but in a way, it's rather remarkable if you think about it, that all the myriad forces that we see around us are really manifestations of four fundamental ones, which, as you know, there is the gravitational force, which all of us feel. When we just drop this, there is gravity, so it's always with us. It was also, as I will say, one of the first forces we understood physically. Then there's the electromagnetic force, which in the 19th century we got to understand better, and which is why we have all these lights and many of these things that all go around us. And then there are these interactions which are much more subtle, which we don't normally encounter, which is the strong interaction inside the nucleus, or rather it's quantum theory of the strong interactions, which is called quantum chromodynamics. I will come to all of these. This is just listing it at this stage. And this is the force, the strong interactions are the force that keeps the nucleus together. And then there is another nuclear force called the weak interaction, which is responsible for radioactivity. And it's the radioactive isotopes that are all around, that in fact are around us in many ways, but are also harnessed nowadays to treat cancer, to date things, and many other applications. So these forces in some sense encompass everything that we know. So you might think of frictional forces, they are ultimately electromagnetic ones. You might think of some spring elasticity, that's also ultimately following from the electromagnetic forces between atoms. So all the forces that we normally might have studied in high school physics are really all in some way or the other manifestations of these. And there are very fascinating stories about how we deciphered the nature of each of these forces and the way they manifest themselves. And it is in some ways still unraveling because there are many complex states of matter in which manifest just the electromagnetic force, and you get very rich phenomena. So, but that's not what I will talk about. In this talk, I will try to tell you a bit, as I said, about why strings naturally arise in all these descriptions of these forces. So that's the thing. So let's go sort of one by one. Gravity, of course, is the most apparent force in nature, and Newton, in some sense, was the first person to realize that it is a universal law of physics. That there is a law of gravitation which we learn in school, the inverse square law of Newton. He proposed that that's a law that governs not only how objects, close by objects on Earth feel gravity, but also how the moon feels the Earth's gravity, and how the Earth feels the sun's gravity, and so on, and different planets and comets and other things within the solar system. We describe gravity essentially through this, and whenever ISRO sends its probes to Mars and Venus, and in the future Venus, and so on, it will be using still essentially the Newtonian laws. But it's very accurate in the solar system, but when we go to the larger cosmos, we learn that Newton's laws are only approximately true, and this is, of course, often the case with many forces. We understand them better and better as we learn or expand our realm. So, for instance, some of the things that Pallavi studies at the level of galaxies and bigger objects, Einstein's theory of gravity is very essential to understand the detailed behavior. This Einstein's theory overhauled our understanding of gravity by encoding it in the geometry of space and time. And maybe if you're not familiar with this, don't worry. I just want to give you a kind of a capsule of what we know currently about the state of gravity. I'll come back to these things. So this is just initial sort of foray into these forces. So then there's electromagnetism on which I want to dwell a little bit for a little while. So electromagnetism is in a sense the interaction which is responsible for most of the things that we see around us. Gravity is important, but essentially describes planetary motion, or in our case, the acceleration due to gravity. But essentially that's it. But most of the other things that we see, the various complex arrangements of matter in solids, liquids, gases, and other forms, these are all governed essentially by the electromagnetic force. It's a very subtle, very beautiful sort of fundamental interaction. And in fact, it was the first case where some seemingly different forces were unified. There was the force of electricity initially. You understand it by the kind of static forces that you feel maybe when you rub against some sort of rough material, or if you have played around with magnets, you see a force, a magnetic force there, and they look very different. But the remarkable thing is that these are really two different aspects of the same force. And this is what the Faraday and Maxwell really sort of brought to light and culminated in the Maxwell's equations, which are central to our modern technology. I mean, everything that we know from motors and dynamos and so on, all rely on our understanding that arose from Maxwell's equations. And not only the electric and magnetic forces, something even seemingly very different, namely light. Light itself, in all its colors, in its spectrum, not only the visible light, but microwaves, radio waves, X-rays, they're all understood now as electromagnetic waves. And this was one of the outcomes of Maxwell's equations, that these electromagnetic waves are created by charged particles. There are electrically charged particles like electrons or protons or other kinds of ions. These electrically charged particles, when they accelerate, they radiate. They radiate light. So in some way or the other, all the light that we see is arising from the accelerated particles. These could be ions, these could be various kinds of charged particles. And this was experimentally understood about a decade or so after Maxwell wrote his equation, and led to, of course, again, many further developments, such as the discoveries by J.C. Bose and others of radio waves, radio transmission, microwaves, and everything else that came in the last part in the early 20th century. So I want to present sort of two pictures of electromagnetism some of you may have seen in school. I would call them sort of the Maxwell picture and the Faraday picture. Most people might have seen the Faraday picture on the right-hand side, because that's the picture you have in textbooks when people place a positive charge and a negative charge. They draw these lines. These lines are what Faraday called lines of force or lines of flux, which tell you essentially where the electric field is, where the electric force is sort of acting. So if you have a positive charge here, and I place some other positive charge here, it will push it towards this negative charge. So the arrows are pointing in towards a negative charge and outwards from a positive charge. And this is also a picture that crops up for magnets also. You could have drawn the same picture with the North Pole and the South Pole, and you would have, and in fact, very often science teachers exhibit these lines in a very vivid way by sprinkling iron filings on some magnet on a piece of paper, and you see the iron particles of iron filings arrange themselves into patterns like this, which is a reflection of the magnetic lines of force. So, Faraday was a very, I don't know if you know the interesting story of Faraday, but Faraday was a very self-taught person. He was actually a workman who learned physics very slowly. He was not educated in a university and so on. But so he had a very physical way of understanding the forces, and he felt that one should, his picture was always in terms of these lines of force. How the lines of force are changing, the dynamics of these lines of force was what he was trying to figure out laws through experiments. And he did uncover many of the laws which went into the discovery finally of Maxwell. But Maxwell actually spent a lot of time trying to make Faraday's picture exact by writing down equations for these lines of force. But ultimately he couldn't. In fact, he thought of these lines, he tried to think of these lines as some kind of strings. And that's where I want to trace the origin, which I will make more precise. He thought of these as some kind of extended string-like objects, and you want to try to find what are the equations that govern these string-like objects. He tried for many years before he realized that it is simpler to think in terms of these field concepts, this electric field and the magnetic field, which I have written on the left-hand side, which is a field in the sense that there is a abstract object, this electric field, which is a vector at every point in space and time, and similarly a magnetic field at every point in space and time. So you think of these tiny arrows at every point rather than the lines. So Maxwell kind of tried to shift the understanding from these lines of force to these arrows, these little points with these arrows sticking out, and he wrote equations for these electric and magnetic fields. So that's what I want to contrast, the picture between point-like fields, these are at every point, versus these extended lines of flux. So Faraday's picture, as I said, was very important for Maxwell, and he was struggling to actually write down equations at first for these lines of force. He, in fact, thought of them as some kind of tubes in which some fluid was flowing, some kind of mysterious fluid, which and these were what you might call vortices. But essentially, these are some kind of tubes of flow. But he never managed to make it very precise, and finally succeeded at, as I said, by talking in terms of these vector fields. Vector fields because they are point-like at every point in space and time. There's an object. There's a quantity. This field, which is itself a vector, and then you write down equations for them. And these are, even if you have not seen them, don't worry, but these are in some sense one of the most beautiful equations of physics, the equations of Maxwell, which now they're called Maxwell's equations, though many pieces were actually found by Faraday, Ampere, many others before Gauss, etc. Maxwell put them all together, and in fact, there was this missing term which was very important, which he brought in. And as they say, the rest is modernity, because that's what, in some sense, governs, as I said, a lot of modern technology until the quantum revolution, which I will come to. But so this is why it was such a big deal, the Maxwell's theory. But so people at the end of the 19th century thought, at the beginning of the 20th century, thought that they had essentially understood everything because they had these equations for gravity, which described the solar system. They understood the electric and magnetic forces, and these were the things that you could really see around you, and light. And so people thought they had everything, but then they came up with a puzzle, because people also discovered that all matter is made of atoms. In fact, Richard Feynman says that if all of civilization were to be destroyed and you were to just transmit one sentence to the future, what should that sentence be? And he said, everything is made of atoms. So in some sense, that's one of the very important insights we have gained, that all matter is made of atoms. But the existence of stable atoms, of which the periodic table gave us many examples, and the structure of that atom, which people like Rutherford and others uncovered, posed a major challenge, because this consisted, unlike what people had imagined earlier, where there were some other models, the picture that really emerged from the experiments was that there are negatively charged particles, the electrons, moving around a positively charged nucleus, which is very tiny, and most of the atom is, as you know, empty space, and these tiny electrons are moving around it. But then it comes in conflict with the Maxwell's equations that I mentioned, where charged particles, if they are going to accelerate, and if you're going around in a circle, so to say, around a nucleus, you are accelerating. Then why don't these electrons radiate light? And if they radiate, they must lose energy, because light carries away the energy. And if you continuously radiate, you keep on losing energy, and eventually the electron will spiral into the nucleus. So how can you ever have stable atoms? So this was a major puzzle. And And at the same time, there was a separate puzzle that seemed to arise where light, which Maxwell and Hertz and others had seemingly demonstrated was purely wave-like, seemed to exhibit in some cases of particle-like nature, which was called photon. So slowly in the beginning of the 20th century, there were all these puzzles about light itself. In fact, there's a little cartoon that I like to show. If you see this in one way, you see light is a particle. Can you see that? Particle. But you can also see light is a wave, right? If you look at it another way. You can't see them both simultaneously. So that's the very nature. And in fact, the exclamation mark also indicates that. There is this very unusual sort of behavior, which was very difficult to make sense of, and ultimately the quantum revolution, which culminated a century ago. We are celebrating this year the 100 years of the full mature development of quantum mechanics in 1925, and that reconciled the wave nature of electrons and protons, as well as the behavior of light, with people like Satyen Bose, of course, also playing a major role in our understanding of the quantum nature of light. And this wave-particle duality is sort of built into the heart of quantum mechanics as it was formulated. So that is a new it really overhauled our idea of reality in some sense, and that's a separate talk about the quantum nature of reality, which I won't really get into, but the classical picture that Newton and Maxwell and Faraday had somehow had to be sort of had to be enriched, or it sort of had to be enhanced in some way to a more subtle quantum description, but which at the same time help to resolve some of the puzzles like this wave and particle-like nature, and the fact that these electrons don't radiate because of the wave nature. It turns out because it's the wave nature of the electrons, and which leads to them being delocalized in some ways, that you actually can have certain patterns of the electrons around the nucleus which do not radiate, which are stationary, so to say. But it needed this sort of quantum description for both electrons, protons, photons, to reconcile all this. And in some ways, the framework that we now understand that does this in a very comprehensive way is what is called quantum field theory. Because as soon as people understood how to describe electrons, protons, etc. in this wave particle-like nature, people applied it to the electromagnetic field, because Maxwell had taught us that there is the fundamental entity in electromagnetism is the electric field, a magnetic field. And in fact, this quantum field theory puts together at the quantum level fields which and their oscillations, which were the waves, the electromagnetic waves, and the excitations of these fields, or in some ways you should think of that the field is sort of bunched together in some places very strongly, and that shows up as particles. And it's very difficult to visualize it. This is a movie which sort of shows how even in the vacuum you can have fluctuations, or due to the quantum uncertainty, in which you can see in some ways bits of the quantum field becoming bunched together and showing up as some kind of virtual, what I call virtual particles. So this quantum field theory framework unifies both the waves of electromagnetism as well as the particles like electrons, protons, etc. So it's the framework in some sense that is in a sense the culmination of our quantum understanding of fields and particles. It was first applied very successfully to electrodynamics itself, because electrodynamics, as I said, Maxwell had this classical theory, but how do you reconcile it with the quantum, this quantum world? And this was the theory which was called QED, or quantum electrodynamics. So it was essentially a theory of how do charged particles like electrons interact with light. How do you correct the Maxwell's equations in the taking into account the quantum nature of the waves and the particles? And in some ways, this theory, which took about 20 odd years to develop from 1925 to 1945 or so, it is still held up as a triumph of the scientific method, because it's a case where this, never mind what this object is, it is something called the anomalous magnetic moment of the electron. There is a object which would have been zero in the classical theory, but is not zero due to quantum effects, due to the Planck's constant. And it can be calculated in the theory up to now about 12, 13 decimal places accurately. It can also be measured in atomic phenomena also very accurately, and you can see almost, I think, till the 12th decimal place or so, which is actually within the limits of the uncertainty on both sides. The terms in brackets are the uncertainties, which is what in both in the theory and in the experiment you calculate in a set of successive approximations. And the theory and the experiment agreed as far as we have been able to measure, consistent with the experimental accuracy and the theoretical accuracy. So it's really a triumph of the scientific method that this very elaborate quantum theory of the electromagnetic field and the particles interacting with it can give rise to these numbers, which you can calculate, which you can measure. So that's in some sense the beauty of science. So this is, of course, was the pinnacle of the development of quantum field theory, and I'll say more about it later. But a reason for this enormous success of quantum electrodynamics was that the strength of the interactions, the quantum electromagnetic interactions, was quite small. Otherwise, it had to be small, of course. Otherwise, we know that Maxwell's theory works for when you want to construct a dynamo or a motor and so on. You don't need to take into account these corrections. And as you saw in that number, the numbers are very small. It started with 0.001 something, right? And that's because there are corrections to the Maxwell's theory, but they are very small. But why are they small? It is because, it's because there is a natural quantity that you measures the strength of the interaction that follows from the electric charge, the Planck's constant, and the speed of light. From them, a dimensionless pure number, you can combine them into a pure number, which is numerically about 1 in 100, approximately 1 over 137. And this number, it's a small number, measures the size of the quantum corrections. That's why, as you saw in that decimal expansion, it started with 0.001. So it's kind of, this is what sets the scale for the corrections. So it's very small in electromagnetism because, and where does electromagnetism come in? Because the charge of the electron is coming there. So the charge of the electron in the natural units is fairly small, and that's why the correction, electrical engineers don't need to study the Feynman-Schwinger-Tomonaga theory of quantum electrodynamics to build a motor, or when the BESCOM people, when they have to repair your electricity line, don't need all these complicated effects. So that's the reason. So this is a case where our classical understanding gets us most of the way. But if you want to be very precise, and there are many cases where these are very important. In fact, where this laser pointer here, this laser requires a lot of the quantum effects of photons to really be so coherent. And as you know, lasers are everywhere. The lasers that are used in eye surgery and everything, ultimately they rely on Bose and Einstein's understanding of photons at the quantum level. So there are quantum effects. It's not that they are very small, so okay, who cares, some small corrections. They are in many situations very important, and things like the laser harness some of those quantum effects which Maxwell would never have arrived at or dreamt of. So in any case, for most things, the quantum effects are small, and the classical description in terms of electric and magnetic fields is a very good first approximation. So let's go back to that picture of the lines of flux. The lines of flux, why were they not very successful? The field description has been very successful, but the lines of flux description is not very successful because, and now in hindsight we kind of understand that, because even when I drew that picture, or when you see these iron filings, these lines are very floppy, so to say. They are not rigidly forming a string. They are extended all over space. So in some sense, the lines, a string is a very localized object, right? I just have a rubber band or a piece of thread. I have a kind of a one-dimensional localized object. But the lines that you have, they're kind of continuous. You have a continuous set of lines in the Maxwell theory, and in some sense, at least as a very impressionistic way, that is the reason why we couldn't, the Faraday's or Maxwell's attempts at actually constructing equations for the lines of flux was not very successful, but the field description was very useful. And in some ways, it is also really related to the fact that the strength of these interactions are very small. The quantum effects are very small. And we'll now see a situation where it is quite the opposite. So I wanted to set this up to kind of tell you why we do have a very good picture for electromagnetism in terms of fields, but it was not guaranteed that it would happen that way. And in some situations, it is not the case. And this is, for that, we have to go to a very quantum interaction, the strong interaction, which I introduced at the beginning. I mentioned at the beginning, it's what holds the nucleus together. The strong interactions are what put a lot of protons in a nucleus. You know that a big nucleus, like an iron nucleus or an aluminum nucleus, has many protons, some neutrons, but the protons are all positively charged. And if it were only electromagnetic interaction, the nucleus would not hold. They would all fly apart because they would repel each other. But there is a force which overcomes that repulsion, and which actually holds the nucleus together very tightly. In fact, very heavy nuclei like uranium and so on are also, they have of the order of hundreds of protons. They are also held together, 92 protons actually. They are also held together very tightly. So there must be something that overcomes this big repulsion that electromagnetism would have predicted. And so people realized gradually that there is a new force, and that's what they call the strong or the nuclear interaction. And now we understand actually protons and neutrons as being made of even more fundamental objects called quarks. So these ultimately are forces that act on these quarks. I won't go into all the details, they're not so important, but a proton is made up of 3 quarks, of of two different kinds. A neutron is similarly also made up of 3 quarks, but slightly different combination. And similarly, many of the other particles that people study in the nuclear, that are produced by nuclear reactions, etc., all ultimately are built out of these quarks, and there's a force between them which is much stronger than electromagnetism. And in fact, now we understand that that force behaves quite the opposite of the way in which electromagnetism behaves. In electromagnetism, like in gravity, the force becomes smaller as the particles are further away, right? I showed the Newton's law. It went as 1 over r square, the force. So as the r, which is the separation, increases, the force becomes smaller. Similarly, in electromagnetism, the Coulomb interaction, as you might have remember from school, also has a similar property. But it is quite the opposite for quarks. Here, the force grows with the separation, and in fact has a very unusual feature that it actually confines the quarks, which is why quarks, while we understand a lot about their properties through very high energy experiments, we can actually probe inside the nucleus and understand many features of the quarks. We never see them individually. They're always in some sense bound inside that proton or the neutron or other such particles. The quarks, if they try to come apart, it requires so much energy that it splits, and new quarks are created in such a way that you get some additional protons or other particles. So you say that there's a force of confinement of these that acts on these quarks, and it's very different, therefore, from the force of electromagnetism, etc. And in fact, the converse is that when the quarks are very close together, they're almost free. So when they're actually very near each other, like inside the nucleus, they actually don't feel much force. It's only when you pull them apart that you start seeing a force. So it's very unusual. And in fact, my advisor, David Gross, who was mentioned, had discovered this phenomena that the force becomes very weak as the quarks become very close. And so, in fact, people gradually began to picture this also like in electromagnetism, but in a slightly with a new twist, that there are again something like a quark and an anti-quark. So having a positive and a negative charge under these strong interactions, and there are lines of flux. But these lines of flux are not spread around. They are actually bundled into a tube which stretches between the two, this thing. And I'll show you just now a movie which actually simulates this based on the actual strong interactions. This is a computer simulation of the behavior of the strong interactions that we, as we now understand it. So the force between the quarks is now coming because you have this sort of elastic tube between these two objects. And so this is this movie which shows that if I try to separate these, there is a sort of a narrow tube between them that forms. These are what I call lattice gauge theory simulations, and they're very precise, very high high performance computing sort of experiments, simulations. And this picture over here is a measure of the energy density. It shows that all the energy is essentially in this tube. So that's what in some sense, the vertical direction is measuring. You get a picture of the field and the fact that as you try to pull it apart, it's like having an elastic string between them. And that's why when you have an elastic string with two objects next to it, when they are very close, it doesn't feel anything. But as you pull them apart, it becomes harder and harder. And if you really give it a lot of energy, it will break apart, but then you'll get two strings. You'll get, which is not shown over here. So in fact, there is an analogous phenomenon people realized even in electromagnetism, which you see only, it's not what you see for usual charges, but there is an analogous phenomenon you see in superconductors when you put a magnetic field in the superconductor, and then you see the magnetic field now is not spread out. It actually forms a similar tube. And there's a deep reason why in some circumstances even electromagnetism shows this kind of behavior. But anyhow, coming back to the strong interactions, people realized around 1974 that you can describe it also by a quantum field theory, which is a generalization of the quantum field theory for QED, the quantum electrodynamics I mentioned, and it's called QCD, quantum chromodynamics, because this force was called the color force for historical reason. Just like you have the electric force, you call this the color force to distinguish between them. And it is described theoretically by a generalization of the Maxwell's equations coming from something called the Yang-Mills quantum field theory, which is a very beautiful kind of an extension of Maxwell's theory. So as an interlude, I just want to, many of you may have heard of this famous scientist Paul Dirac, who was one of the founders of quantum mechanics. He tried to actually think, even independent of the strong interactions, he was thinking even in fact, that he has some lectures he gave in Tata Institute in Mumbai around 1955, 1956, in which he was trying to understand even electromagnetism in this Faraday-like point of view. And he says that we may assume that when we pass to the quantum theory, the lines of force, which we drew earlier, become all discrete and separate from each other, and we now have a model. He wanted to construct a model in which the basic entity is the line of force, which is a thing like a string instead of a particle. And he says the strings will move about and interact with one another according to quantum laws. So that was his vision, his picture, which he couldn't realize in electromagnetism. So he wanted to go back to the Faraday picture of understanding the electromagnetism in terms of this lines of force, but he didn't fully succeed. But as I will try to this picture is now realized in the strong interactions in this kind of setup is where is the natural place to understand this Faraday-like picture in the quantum theory. So that's why so that introduces that gives you a motivation for why strings are important. Understanding string-like objects were important. This question naturally arose in the strong interactions and in some ways foreshadows something in the electromagnetic interactions as well. Now, when people try to understand these theories of the strong interactions, very similarly to how they try to understand the quantum electrodynamics, they realize that there is a difference. And indeed, you saw qualitatively also there was a difference, right? There was this, unlike in electromagnetism, now the lines of force are all bound together. And that's because the corresponding strength of the interactions, which was 1/137 in electromagnetism, that was the strength of the quantum effects, is now order 1 in the strong interactions. This is why the strong interactions are inherently a quantum force. The force, there is no classical description of the strong interaction. It is a fully quantum interaction that you see in the nucleus. The quantum effects, this means that the quantum effects are as important as the classical effects. So in other words, there is no way in which you can say, oh, like in Maxwell's theory, there is the leading piece you can describe by some Maxwell classical picture, and then there are small corrections of order 0.001, etc. It's not the case here. The corrections are order 1, the same size. So there's no meaning in separating a classical picture or from a quantum picture. So the kind of intuition that was there in electrodynamics doesn't apply in the strong interactions. And this is why people returned to this lines of force picture of Faraday. And this is now potentially a very useful way to understand, if we can understand the equations for these strings. So now the picture has sort of turned. Now the Maxwell-like picture in terms of fields is not so useful for the strong interactions, but the Faraday-like picture is perhaps much more important, because these seem like the basic entities. Even though the quarks are there, they're interacting so strongly, but the strings, maybe you have a better chance to understand the dynamics of these strings, because as you saw in that simulation, they're really like string-like objects. And that's something even in fact, if you have studied in high school, people talk about the physics of a vibrating string. So it's relatively easier to think of equations for these strings. And in fact, there was an initially success for this, never mind the technical details, but some of these quark, anti-quark bound states, the things called mesons, they were their masses were very close, and still are. You can look at the table of their masses, and they seem to be governed by the harmonics of a relativistic string. It is to be not the non-relativistic string that you study in high school, but a relativistic generalization of that. And but then there were other properties that seemed to disagree with this simple string picture when people thought of just a string moving in our space-time. That didn't seem to agree. Now, so that seemed like a bit of an impasse, that there was this attractive picture of the strings, but you couldn't really capture very much about the behavior of the strong interactions just from a simple naive picture. And this is what has changed. But to explain that, let me just so the resolution to that is that even in the movie that I showed, or even the picture that I drew, that string was a very fat string. It had some thickness. So in some sense, when you model a string, you normally think of an idealized string, which is just a one-dimensional object, has no thickness. And so the idealized thin strings that you might try to model them, that didn't quite capture everything, because at some level, the string did seem to have a thickness. And and people thought maybe that's the reason. The interesting thing, and so people didn't have detailed equations that for the strings which could capture the behavior of the strings of the strong interaction. But in the last 2 or 3 decades, we have realized in a very remarkable way how to overcome this barrier. And the picture is roughly as follows. This was that fat string that I tried to draw earlier. The picture, which is, you have to take a bit of this on faith from me. The picture is that this fat string can be viewed as a shadow of a thin idealized string, but in effectively an extra dimension. And an extra dimension meaning a curved space-time, which I will talk about soon. But at the moment, think of this as our world, and it's as if the string that we see is a shadow of something that in which our world is just a kind of a screen of an extra dimensional space-time. And quite remarkably, the equations for these idealized strings in this 5-dimensional or higher dimensional curved space-time, something called the anti-de Sitter space-time, seems to capture better the properties of these strings of the quantum chromodynamics. So that was quite striking, and I'll try to explain to you why, because this will then connect with the other force which I didn't talk about till now, which was gravity. And I've now brought it in. I smuggled it in the last slide because, as I said, this is a curved space-time of the kind that actually is described by Einstein's equations for describing curved spacetimes, which capture gravity. So somehow, this describing the strong interactions seems to know something about gravity, which seems at first sight very different. And this is so this is how the gravitational force enters the stage. And in fact, it enters in a kind of a very interesting way, because independent of all these developments that I was talking about, people had been studying the gravitational force at the quantum level. Because as I mentioned in the beginning, Einstein tried to describe gravity going beyond Newtonian theory in terms of equations for a curved space-time. It was actually also can be viewed as a generalization of Maxwell's equations, but like Maxwell's equations, it's a classical description. And the corresponding field is something called the metric field, which describes the space-time geometry. But if you try to now use the same ideas that people used in electrodynamics, where they quantize the electric field, you use it for this metric field, and the corresponding object, the graviton, the quantum field theory machinery somehow breaks down, and in ways that seem very mysterious, but at some level also kind of understandable, because unlike all the other forces, gravity seems to have to do with the dynamics of space and time itself. This metric field is capturing the geometry of space and time. So the meaning of the geometry at the quantum level is a very mysterious concept, which quantum field theory doesn't seem to have the ability to capture that, as far as we know, at least in the usual way. If you try to just follow your nose and do the same sort of things that you did in electrodynamics, it doesn't work. But around the same time as the strong interactions were understood, people also made independently a very novel description, because they were studying these strings for understanding the strong interactions, but then they realized that amongst the excitations of a relativistic string, in particular what is called a closed string, like a rubber band like string, many of the strings that I showed you were like open strings. They had two endpoints, what are called open strings, but you can also consider a rubber band like string, which is a closed object. And they found that amongst the excitations of a closed string is the graviton, the analog of the photon. And if you consider the interactions of the graviton in the context of the interactions of these strings, they are perfectly finite. They don't lead to some of these what I call untamable infinities. So there is a framework in terms of the relativistic closed string that seems to capture the behavior of gravity at the quantum level. And in fact, there are well-defined rules for the interactions of the strings. Now, instead of what are called Feynman rules for particles, you generalize them to these closed strings interacting. So this is, if you wish, a space-time picture. You should think of at any given time, there are these string-like objects, but then this is like a movie of the whole space-time history of the interactions of these strings, just like Feynman drew similar pictures for the space-time history of particles. There's a generalization to those of strings, and this at some level seems to be compelling as a right framework for a quantum theory of gravity. So what am I saying? That from two different corners or two different sides. People who were studying Einstein's theory at the quantum level to understand gravity, and people who were studying Yang-Mills theories to understand the strong interactions. For both of them, the string-like objects seem to very naturally arise. So that is a rather remarkable thing, that you are interested in understanding two different sets of interactions, but ultimately they seem to rely on understanding these string-like objects that are in some ways present in both these theories. And what has now, in the last 2 or 3 decades, been better understood, that the same framework captures both these kinds of strings, these open strings that correspond to the Yang-Mills theories, and the strings that correspond to the gravity. And this is what goes under the somewhat obscure name of the ADS-CFT correspondence. But one of the remarkable insights is that these Faraday-like flux tubes, you can write down equations for them, and they are equations for strings in this 5-dimensional space-time that I drew a few slides back. And those equations reduce to actually Einstein's equations in some limit. So the equations describing the flux tube are related to Einstein's equations, or their generalizations in terms of strings. And it's quite interesting that both these string-like pictures kind of merge into one. And so people now have been exploring how to understand both quantum gravity, namely properties of space-times like this anti-de Sitter space-time at the quantum level, and they describe it in terms of these Yang-Mills theories, because that's one way you can connect. The pictures are equivalent. You can either use the gravity picture to describe the strings in the boundary in the quantum field theory, or you can use the quantum field theory to understand the gravity. And so people have used this picture the other way around, to use the quantum field theory to describe aspects about gravity like black hole entropy, and it explains many puzzles such as the Hawking-Bekenstein entropy, which is the subject of a wholly different talk. So what I'm trying to say is that very basic questions in the theory of gravity are explained in terms of these equations that govern these flux tubes in a quantum field theory in one lower dimension. The picture that I draw earlier, I just want you to recall that again, the quantum field theory. Let me just go back again, yeah, just to put that in your, oops. So this was the quantum field theory lived in this 4-dimensional boundary. It's like a hologram, as they say. And then there was the quantum space-time, which is the 5-dimensional space-time of which this is the boundary. So you can either study questions of quantum gravity in this space-time using the quantum field theory on the boundary, or vice versa, you can understand the equations of the quantum field theory in terms of the strings in this higher dimensional space-time. Depending on the regimes, you can, this is like a two-way sort of, it's a two-way street, and each side teaches you about the other, because it's quite remarkable that there is even a connection between the two. So, so let me, so that's, so I want to sort of leave you with that picture. And in fact, one of the things that I have been trying to do is to derive this gauge string duality from first principles and see the string picture of the higher dimensions emerge from the quantum field theory, and I think that is now within reach. There are, for the young people, I just want to flag a very interesting aspect of this connection, which has to do with quantum information, because this unraveling this hologram, which is depicted here, this is the same picture. This was that boundary, that hologram, and this is the higher dimensional space-time. This picture that quantum space-time emerges from this quantum field theory has many interesting things to say about aspects like quantum entanglement in the quantum field theory and how that is encoded or gives rise to the geometry of space-time. In some ways, you can ask, are Einstein's equations capturing the flow of quantum information in some sense? And these are very cutting-edge ideas in quantum information and computing these days. So just wanted to tell you that this remarkable connection can have a lot to teach us conceptually about things which are going to probably play a role in technological development as well, namely understanding better notions of quantum entanglement and quantum information. So let me just conclude by saying that this lineage of strings goes back to the flux lines of Maxwell and Faraday, and it's an alternative to the field description that people have worked with for many years, especially forced on you when you consider these Yang-Mills theories like for the strong interaction. And the equations governing these strings appear to be higher dimensional. The natural way to describe them seems to be higher dimensional, and that was the surprise. And in fact, it connects very naturally to the strings that describe gravity at the quantum level. And the overall picture is that of a sort of a emergent picture of quantum space-time from these strings, which are playing the role bridging that quantum space-time and the quantum field theory. So thank you for your attention.
Please raise your hands if you have questions. Bring the mic to you.
Thank you. You must be exhausted. So, the cumulative of human intellect, classical approach and the quantum approach. The cumulative of human intellect still lags behind what the universe really wants to imply. So, is it acceptable that we have to leave the way the human thinks and go the way the universe is designed and parallelly to anything? If the universe is functioning, so the universe must be having an algorithm parallel to its functioning. So should the human civilization leave the anthropogenic attitude, the intellect, and go to the intellect, the universe, to understand what really is the universe?
But it was difficult for us to leave whatever we are, right? I mean, how do you, in practice, whatever we are is by definition anthropogenic. And it is our best way to try to decipher the universe. And it is, the remarkable thing is that how much we have been able to expand our sphere of thought. I mean, from very basic notions of how a ball falls or moves, which are at least things that are visualizable. We are now talking about, I mean, the framework of quantum mechanics, the framework of Einstein's general relativity and curved space-time. These are things which are in some sense not natural to human beings, meaning they're not something you would immediately come up with. They have been arrived at by expanding our conceptual frameworks. And that process is what is continuing here. And these remarkable connections are ways in which our minds are expanding. And through a lot of it, which I didn't, of course, bring in, is through the language of mathematics, which is ultimately at some level, perhaps at least there is always a philosophical debate about this, but mathematics in some sense exists perhaps independent of human beings. And we are in some ways using that universal language of mathematics to expand our understanding beyond what our sensory descriptions tell us. So at some level, mathematics is the tool that helps us to escape, as you say, from our anthropogenic limitations.
There was this paper like 1 or 2 years back where a bunch of entangled particles were sent through a quantum computer, and that is like analogous to
wormhole.
yeah. So what is how is entanglement sort of related to space-time? Like,
Yeah, it's a very speculative notion. I must still say it is not completely accepted. Also, at least the interpretation is not completely accepted. I mean, they did some simulations and you see this, but it is coming from this idea which I was hinting at in the last, my penultimate slide, which is that this connection between so when I say, does quantum entanglement give rise to the geometry of space-time? Essentially, there are hints that the entanglement that you see in that quantum field theory on the boundary, which can be in some cases just plain quantum mechanics of some qubits. That's why, in fact, there are these zeros and ones here to kind of think of them as some qubits. But they are, in some ways, there's an equivalence between that description and this description in terms of geometry in the higher dimensional space-time. This which are described by Einstein's theory. So one interpretation people have put forward is that the kind of entanglement you see between qubits, especially when you have many of them, could be alternatively viewed as a geometry which is like a wormhole. A wormhole-like geometry is a kind of a curved space-time geometry. It is, roughly speaking, what the word says. It's some kind of a tunnel between two different space-time regions, and you can find solutions of Einstein's theory which have that feature. And so there was this famous slogan called ER equals to EPR, that EPR is the Einstein-Podolsky-Rosen entanglement, which is one of the very unusual features of quantum mechanics, quantum field theories. And ER is actually something that Einstein and Rosen did around the same time, which is these wormhole-like solutions that maybe these two are related. As I said, there are some indications of this, and people have tried to kind of give some evidence through quantum simulations of that, but I think it's still a little premature. That's why I wanted to leave it as questions which are at the moment being explored. And so can Einstein's equations capture this flow of quantum information, etc.? These are things which are really actively being explored.
Sir, you related strength of interaction parameter
Yes.
in QCD and electromagnetism.
Yeah.
And you said QCD is like more of quantum.
It's very quantum, highly quantum.
But for example, an atom is
Yeah.
mostly an electromagnetic interaction, at least
Yeah.
the atomic structure. So you want to call it as less quantum because we don't understand an atom without
Quantum mechanics. Yeah. So it is true that atom's existence is highly quantum, and to understand, you're right, to understand the detailed structure of the atom, you don't need, you need quantum mechanics, you need the Schrödinger equation, etc. But what I meant to say was, if you are generally just looking not at that atomic scale, so when you go to very small scales, you do need to take into account quantum effects, because that is not the only parameter that enters. There is what is called the action, the Planck's constant sets a scale also. So you need, and as I said, even this laser is a quantum effect. So there are situations where the quantum effects are very important to understand the behavior. But for why I was trying to answer the question, why were Maxwell's equations so successful? Why did they describe everything? People construct all of our electromagnetic infrastructure without studying quantum electrodynamics. I was trying to answer that question, that this strength of interactions is what measures the corrections we would need if we were to do it at the quantum level. So most purposes you can ignore that, but some cases you cannot.
Sir, why do you need 13 dimensions in string
13,
theory?
no, I didn't mention the word 13.
But
I mean, here I mentioned only 5 actually, one extra dimension. One extra dimension, actually there is an interesting kind of interpretation of that extra dimension. It is the energy scale that you are probing things. In fact, even in quantum field theory, people had understood much before all this in the 1960s, even in the context of condensed matter physics, etc., that the physics, when you are probing at some energy scale, there is an effective description that is sort of scale dependent. It depends on so even the strength of the interactions depends on the energy scales. And in some ways, this extra dimension geometrizes that energy dependence. So it's like you can think of that extra dimension as, from the point of view of the quantum field theory, as stacking together many quantum field theories at all the different scales together. When you put it, that's what forms that extra dimension. It's a rough way of this thing. It may not make very much sense, but roughly wanted to say that that extra direction is a measure of the scale, energy scale or length scale at which you are probing things. That's why, in some sense, in the boundary, what looked fat was very thin. A fat string was really a shadow of a very thin string. So it's a question of the resolution at which you probe things.
Hi. Oh, so my question is on this simulation, first simulation.
On the
First simulation, like Dirac and so on. So
The
where
movie.
particles are just colliding each other and
this movie of this
first simulation.
the fluctuations. I think it was.
Yeah, this one.
Uh-huh.
So which color represent which one? There's a blue and yellow is.
Yeah, I mean, I'm not very sure about the color codings. I think they represent different energy scales again.
Not particle and light.
Not quite. I mean, these could be particles of different kinds. I suspect he is probably simulating the simplest kind of particles, which are what are called scalars, and these are just fluctuations of different energy scales. Can be very high energy particles, very low energy particles. I think that is what the color coding I suspect.
So they are not colliding each other, huh?
They can, some of them you see can kind of merge with each other. In the vacuum, all such processes are possible of virtual particles. And like this QED, the framework of QED tells you through this mechanism of Feynman diagrams how to visualize all these processes or how to take into account the sum of all these processes.
So that is elastic or inelastic collision?
You can think of them as elastic. I mean, ultimately, inelastic collisions are just where energy is carried away by something else. But if you're taking into account all the different things, then energy is conserved within that system. So,
okay, so like one of the book I read before, there is written, if we understand fully the nature of light, like its wave or particle, so we have to first understand the collision between light and electron. So the collision between, if you have any idea of collision between light and electron?
Yeah, that is what Feynman and others understood in the theory of quantum electrodynamics. And I had a picture in a slightly different context, but essentially that's what the Feynman rules calculate for you. The I think, let's see, in the next slide. Yeah, so you can think of these as electrons and this as a photon, and there's very definite rules for talking of the collision of the electron with the photon, and that is what people, I mean, this is a mnemonic, it is a picture, but it captures exactly what the calculations, these are various space-time processes that you include. This is a kind of a bookkeeping tool for including what you might pictorially think of as collisions between these particles. And there are, it tells you what is the quantum amplitude for each of these individual things to occur, and you put them together to compute the probabilities or amplitudes of some processes to happen.
So after colliding, they merge or they just separate?
It can do many things depending. In this case, there are two electrons are coming, let's say, and they exchange actually a photon and then they go out. So it's really capturing in some ways the scattering between two charged particles. But you can look at many processes, and each process that is allowed by the basic interactions, you can compute what is the probability of something happening.
Oh, sure, sir. Thank you.
I think maybe someone else, yeah.
Hello. Yeah. The movie you just showed, right? Like the one that you mentioned that it's in vacuum, correct?
Yeah.
Wait, is that similar to your quantum foam?
No, this is just the quantum field theory. The quantum foam is an idea that people apply to the space-time itself, and it's a speculative idea, or it's really only a picture, I would say. I mean, you can say that the space-time geometry itself is fluctuating. Here we were talking of something like electric field or magnetic field or some other more field which exists on top of the space-time that was fluctuating, but the space-time, this, if you wish, this background is the space-time. That lattice that you see, grid at the back, is the space-time. The space-time is not fluctuating. If the grid itself were to fluctuate, then you would talk about some quantum foam. But it is the rules for the fluctuation of that grid itself that we don't understand.
Hello, sir. Maybe a slightly philosophical question, but what do you think about emergence as a phenomenon? As in, to be very specific, classical interactions are an emergence of quantum level interactions. So I have an AI background, so when I think of it, you know, when we know the interactions at neuron level, but when we throw a lot of compute and try to, you know, just scale, the scaling laws per se, a lot of things emerge. So do you think a parallel can be drawn into, saying that classical phenomenon is an emergence of quantum level phenomenons? Another case in point would be, let's say, game of life, cellular automata, right? Mm-hmm. So I just need to know about your thoughts, what are your thoughts about it?
I mean, the notion of emergence is very much there in physics and in many systems, complex systems. That does happen. I mean, we do have basically, again, simple atoms come together and interact to form very unusual, complex structures, including life itself, for that matter. So some of that is the notion of emergence there is that you have a very different description at that emergent level compared to the microscopic level. which is in terms of atoms and electrons, etc. But I'm not very sure you would call the classical picture an emergence. I would say it is more it is more an first approximation to the quantum picture, at least in most situations. The classical picture, when it exists, when it arises, is something that is a coarse description, but it is, I mean, it's not qualitatively, I would use I think I would set a high bar for the application of the term emergence when some qualitatively new feature arises, which is very different from the underlying microscopic picture. Here, it's not the emergence of classical phenomena from the quantum phenomena, where it does happen, is not quite like that. It is more that it's a rough approximation. It's like a first approximation to it's the same phenomena. You still talk in terms of electrons or electric fields, magnetic fields, charged particles, but the Maxwell's equations are the 0th order description, but if you want a better, finer description, you need to include the quantum effects. So it's in that sense, I think there's no new this thing that's really coming out. The chaos, did you say? Yeah, I mean, it need not, the classical description need not always be chaotic, but it can sometimes be there. So I would say more that, yeah, in terms of computation, it is perhaps the coarse sort of description of the computation, where you think of, instead of qubits, you think of bits in some sense. You kind of collapse the whole thing into a smaller, like a less refined description.
Good evening, sir.
Yeah.
Infinite appear when we try to which are not complete.
Okay.
To set a high energy cutoff and then
yeah, that's the technical difficulty that people have faced in trying to do the same things as people normally do in quantum field theory, that you can't, I mean, if you try to naively do that, you seem to have to include more and more corrections in the UV to sort of, there's no real sort of way in which you could complete it in that sense within the standard quantum field theory. At least as far as we know, there are people who speculate about some non-trivial fixed points and so on, but I think it's fair to say that by and large we don't know how to complete it, because the completion would require an infinite number of terms seemingly, whereas in most of the other descriptions for the other forces, you can do it with a kind of in a finite way.
So we have some questions from the online audience. We'll take that as the last question, one of them as the last question. Sure. What is the role of gauge theories in quantization in quantum field theory, and how does this connect to string theory?
So gauge theories are a special kind of quantum field theory. I didn't emphasize this well enough because I only talked about the only quantum field theories I talked about were gauge theories. So gauge theory is just a term, and Maxwell's theory is the simplest example of a gauge theory. These generalizations that are called Yang-Mills theories are also what are called gauge theories. Never mind the term itself. These are some of the most special quantum field theories, and the weak interactions, which I didn't actually talk very much at all about, is also a gauge theory. So all the fundamental interactions at some level seem to be described by gauge theories, except maybe gravity at a complete level is not. It has a certain relation to gauge theories, but it's not one of the simpler gauge theories. But to answer your question, so in general, it seems as if a lot of these gauge theories can be related to string theories via the kind of connection that I drew, because all gauge theories have some kind of lines of flux underlying them, and especially when they are strongly interacting, the natural description is in terms of these sort of Faraday-like strings. So in that sense, I think a lot of gauge theories can be reformulated as string theories.
Okay, thank you. I'm sure a lot of you have a lot more questions to ask him. So before that, let's thank Professor Rajesh Gopakumar. And the Kaapi part of the Kaapi with Curiosity is served outside. You should meet Professor Gopakumar and ask him over Kaapi. So let's all head to Kaapi.